All right. So we're going to take a look at kinetics. When I get it started properly. There we go. Chemical kinetics.
Kinetic motion.
In a manner of speaking, right? Chemical kinetics is a little bit different than kinetics in physics. Physics kinetics is just purely something's moving. Chemical kinetics is a little subtler than that. Things are moving, that's true. But we want to measure how things are moving, not in terms of absolute velocities, absolute velocities. We want to know how the reaction mixture is changing in its composition. So this is the general equation for, this is a general equation for describing a reaction rate. And that's what we mean by kinetics in chemistry, reaction rate. How fast is the reaction proceeding? There are some reactions that will eventually happen. It's just they happen so slow, you and I probably won't live long enough to see it. Okay. One way of expressing the reaction rate is the change in concentration of either the reactant or the product. It doesn't matter really. Over a certain time period. So we measure the concentration at the end. If A is, well, actually, yeah, at time T2, which would be the latter time, and T1 would be your beginning time. So whenever you start, the concentration is here. When you end, it's here. And this is how much time it took to get there. So the ending time minus the beginning time. Of course, if you start at time 0, then your change in time is equal to T2.
So it's basically like in physics, your initial and final velocity, but this is initial time and final time?
It's similar, yes, it's similar to that. So we would say the rate then is equal to a change in concentration of some component, and that's what we mean by square brackets. Square brackets means concentration of whatever's inside over a particular period of time. And if you subtract the beginning from the ending, then if this increases, that value is going to be positive, right? Because the end is going to be, this one's going to be bigger than that one. But if you're describing the disappearance of something, and A starts out at a concentration here, and ends up less than that concentration here, that means the second term is going to be larger, and then this term will be negative. Right? So negative designates a disappearance of something, and positive the appearance of something. Okay. And a common concentration unit that we use is moles per liter or molarity. Okay. It doesn't have to be the only one, but we're going to kind of stick with that. Particularly if it's in solution, we're going to say moles per liter. If it's a gas, we might say moles per liter, right? That's valid. Or we might say partial pressure, and then there'll be a relationship that we can draw between the two. And we'll get to that later. But those two will dominate, either molarity or partial pressure. So here's an example of a reaction that we measure as the reaction progresses. Right? We start at time 0, and then over this amount of time, we're showing that this reactant produces these two products. So this NO2 starts out here, and of course we have no NO and no O2 to begin with. And gradually these two appear in greater and greater amounts, and this one disappears, becomes lesser and lesser. So that would be a data set for tracking a reaction progress over a certain period of time. And yeah,
Does it count for any one, not just nitrogen dioxide?
it's different for each one. Right.
Oh yeah, I didn't notice all those in there.
Yeah, and the temperature is important also. So you need to specify the temperature, and you need to specify the reaction if you know it. Sometimes a reaction is investigated when you really don't know the overall reaction. And the whole purpose of studying the kinetics of the reaction is to determine what the reaction is, how to describe it in these terms. But in this case, for illustration purposes, we know the reaction is this. We know that every time you lose two of these, you get two of those and one of those, right?
What do you mean by that? If you lose that?
If you lose 2 moles of these in progress of the reaction, you're going to get 2 moles of those, right? Because it's 2 to 2. And if you lose 2 moles of these, they're going to show up here. Here's 1 mole of those. So you're going to get 2 of these and 1 of those for every 2 of these. It's just simple reaction stoichiometry. Now this is a little hard to see, so I'll try to explain what each one is. The red one stands for oxygen, and the blue one stands for nitrogen monoxide. So in the beginning, we start out, these are products. So at the beginning of the reaction, you got nothing. There's 0. And you've got whatever the concentration happened to be at the beginning for nitrogen dioxide. Okay? So over time, this one decreases at a certain rate, and these increase at a certain rate. What you may know, if nobody's had any calculus.
I had pre-calculus.
Yep. Okay, you may understand this then. The concept of instantaneous velocity, or instantaneous rates, or instantaneous slope. On a curve, well, we know on a straight line it's rise over run, right? But on a curve, the slope of the line at a particular instant or a point on that line is the same as the tangent to the line. Okay? So the rate is the tangent to that line, and as you gradually progress through the reaction, notice that the slope becomes less and less and less negative. It flattens out. So the rate slows down. Okay? And it speeds, it's really fast here in the beginning for this one and for these. The disappearance of this one and the appearance of these is really fast because the slope of the tangent to the line is really steep. Right? But as the reaction progresses, the curve flattens out. And that means that the rate is decreasing. Either increasing, showing up amounts, the rate decreases, or disappearance, the rate decreases. Right? So what that illustrates is, as the reaction progresses, in this case anyway, the rate of the reaction is not constant. It changes with the character of the composition of the reaction mixture. Right? That's the whole point of this one. And that's what we mean by instantaneous rate. That's the rate of the reaction at any particular time. And it's always the tangent to the curve. Okay, so now we're going to express this reaction in terms of a law. Remember, laws just say this is what happens. Doesn't explain why. So all we have to do, and in this case, for kinetics, the laws are always mathematical. Right, so we're going to say for this one, we're going to express it in terms of the disappearance of NO2. So the amount or the concentration of NO2 is the rate of that reaction expressed as the concentration of the NO2 times some constant value, and that constant value has to be determined experimentally. You can't determine it from the reaction. It bears, at this point, overall reactions, it has no, this has no impact on that. You can't derive K from the reaction. You have to determine it experimentally. And then there may also be a power associated with that concentration. Okay. So this is known as the order of the reaction. Okay. Concentration and then this constant. So that's a general expression for any rate of reaction for one in which we only have one reactant. Right. If we had two reactants, we'd have to introduce something more complex now before you got a good handle on the concepts.
Will we be doing that?
Yeah, we'll do that. It's easier to tease out information from a reaction if you can limit the expression to just one reactant. And when we do our lab next week, we're actually going to have two reactants. We're going to have a dye, a food dye, and we're going to have bleach. And the rate of the disappearance of the color is a measure of the reaction that's taking place. But since we have two reactants, we have to use a concept called a pseudo rate law. So what you do is you make the bleach concentration so high that it doesn't change. Right? And then you focus on the color. And then you find out, you get your information about the rate of the disappearance of the color. Then you use that and you go back with a second experiment, different bleach concentration, and then you tease out the information from bleach.
So both ways you think bleach to the way it's constant.
Say that again?
So bleach would be the constant in that situation?
Bleach would be, in a manner of speaking, the concentration of bleach then would be embedded in the constant. Yes, right. So the K value, instead of being a K, we call it a K prime because it's not the true K. We're going to embed the concentration of the bleach in that first, and then we'll find out, we'll pull the K prime apart and find out what the kinetics of the bleach is. Then we can put them both together in an equation. Okay. But for now, we're going to concentrate on reactions that truly only have one reactant. To keep things simple in the beginning. Okay. Here's another concept that we use to try to simplify things. Chemical kinetics, the more I look at it, the more it resembles art as much as science. There are a lot of things that you have to do, you're forced to do, in order to gain scientific information about the reaction. One of those is, here's a concept. Let's just say we have one reactant and it's making one product. Just keep things simple. What happens is that in the beginning, of course, you have no B, only have A in that scenario we're setting up. So A starts producing B. Well, the more B you get, the more pressure there is for the B to go backwards. Right? It may not be at the same rate, could be at a different rate, but you will get a pressure for B to come back to A, the reverse reaction. The problem with that is, in kinetics is, how do you know
Which one's first?
Right, how do you know where you are in the reaction, right? So what we do is we keep it really simple. We say, all right, we set up the conditions So only the forward reaction is important. And that's called the study of initial rates. So you set it up so that B is 0 to start with, and A is something. And then you study the rate at the very beginning, just the very beginning of the reaction, and you tease out information about the reaction based on just that. Okay? That's why in this rate expression, there are no products, because we study it under conditions where the reverse reaction does not affect the overall rate. If we go further down the line, then we would have to consider, for the rate law, the reverse reaction. Okay. And this just reiterates, the value of this exponent, the order of the reaction, also has to be determined by experiment. You can't write it from the balanced equation.
What's the first thing you try to solve? Is you solve for n first, or you try to solve for k? K velocity.
Wouldn't n be like an exponent? Not an exponent, but like.
N is an exponent, yes.
Okay, make sure.
Yeah, but we call it the order of the reaction. But it is an exponent, true.
Okay, wouldn't you solve for the exponent first?
As a matter of fact, we do. But it's not a mathematical solution. Not strictly speaking. We're going to learn to recognize from the information that's given in a reaction, a series of measurements. We're going to learn to recognize what order of the reaction it is based on that information. Okay, so that's coming. Okay, before we get there, there are two ways of expressing a rate law. One is called the differential rate law, and this all goes back to calculus, and I've got some handouts. I think they're on Blackboard. That'll show you how the differential is related to the integrated, because they're both expressions of the rate law. They're just expressed differently. And depending on what you're going to use them for, sometimes it's easier to solve the equation with the integrated rate law than it is with the differential. So this, yeah.
Do they have two different formulas?
They have two different forms, yes. Yes. So this one simply shows this, how the rate of the reaction depends on the concentration. Right? So if you know that, then if you plug the concentration in here, then you'll get an expression for what's the rate of the reaction at that concentration. Okay. With the integrated rate law, it shows how the concentrations vary depending on time. Right. So this has no time, a separate time variable in it. This one does not. You have to solve this part before you get the time over here. But with the integrated rate law, there are variables over here on this side that introduce time, and the answer that you get is not the rate, but I think it's concentration. I'll show you an example. Okay, so this is just summarizing what we just said. We're going to study reactions at the very beginning where the concentration of the products don't matter. They don't influence the rate. If you determine it, depending on which one is easier to do, the differential or the integrated, once you know one, you can create the other one. Right? They're related. So once you've got information from one form, either the integrated or the differential, you can write the second one. So typically you pick the one that's easiest to do with the experiment you're conducting. And then you can write the second one. The value of a rate law for a reaction is of particular interest to chemists, because if you know the rate, very often you can deduce or infer individual steps involved in a reaction. And when we write a reaction equation like that, whatever it happens to be, reactants, yield, products, this is an overall reaction. There's a lot of stuff going on in here that you don't know. Steps, in fact. This might go some here, it might go here, and then it might go over here, and it might go up there, finally. Several steps in the reaction. And the rate laws and the rate investigation helps you deduce what those steps are. Now, how do we do that? Like I said, it's an art. The best way to do it is you propose different steps that will get you from here to there. As many as you can think of that are reasonable. And then you go back to you design your rate experiment, you conduct the experiment, and then you use that information and say, all right, I've got 6 possible we call them mechanisms. 6 possible stepwise progressions from reactant to product. And then you look at these and the information that you get from your rate experiments, and you say, that's stupid, that can't possibly work. This one maybe, but if these 2 are true, then these 2 can't be true. So you have to make a decision. All right, so, okay. So my rate also tells me that 1 and 4 are the most likely. You just keep narrowing it down until you finally get to one that is the most reasonable. That's the best you can do. It's rare that you can say definitively, these are the steps of the reaction.
So is this like proofs, kind of? No, I don't know why I'm putting some proofs for this.
In a manner of speaking, yeah. I mean, it's not.
I don't know why.
It's not as regular as mathematical proofs. Right. But yeah, the concept is similar. What we're doing really is process of elimination. You throw out the worst ones, kind of like Sherlock Holmes. You know, with all the possible scenarios, you eliminate the impossible, and whatever's left, no matter how improbable, must be the truth. Okay. I mean, that was Sir Arthur Conan Doyle speaking through Sherlock Holmes, but it's made for a good novel or two. Anyway, okay, so we have to determine experimentally the order of the reaction. So we need to know how to do that. So we have method of initial rates. And that's what we're going to focus on to determine these orders. So we determine the initial rate at the same value of time, very close to time 0 as we can get. Some reactions are so fast, they actually couldn't be studied for the longest time. Right. It wasn't until the advent of lasers where you could actually watch a reaction on the millisecond or the microsecond scale. And some of these reactions you could finally see what was happening. But you try to get as close to time 0 as possible with your rate determinations. And you carry out several different experiments with initial concentrations of each of the reactants. You may have more than one reactant, right? So what you do is you set up your experiment so that if you have, let's keep it simpler, say we have 2 reactants, right? and they're going to produce some products over here. So for experiment 1, you might have a concentration of, let's just pick numbers, say 1 and 2 here. And then for the next reaction, you'll have 2 and 2 concentrations. And then for the third reaction, you'll have 2 and 1. So in order to determine what's happening with A, you're going to compare this reaction experiment with this reaction experiment because that one is constant. And then in finding out what happens between this one and this one for B, you use these two experiment results because that one's constant.
Wait, how do you know it's constant?
It's constant because I said it was.
Oh.
Yeah, I set the experiment up so that these two are constant and that one's not, and these two are constant. These are separate experiments, right?
So what was that 2 in there, constant? What was that 2? 2 is constant?
These are just, I just picked those as concentrations, right? So at this concentration and that concentration, you get a certain reaction rate. And at this one, you get another one, at this one, you get another one. And then you compare these two. And I'm going to show you how to do that. You compare these two for what's happening to B, because those are constant. And then you compare these two to find out what's happening to A, because B is constant. Okay. So here's what a reaction with 2 reactants would look like as a rate law. You have a constant, and that constant is for the reaction itself. This is the true constant. This is not the pseudo constant I was talking about earlier. This is the true constant. And then we have this reactant to its power times this reactant to its power. And these concentrations vary, like our 1s and 2s before. And then these powers are independent of one another, but tied only to the particular reactant. Right? So this is the order of this reactant, this is the order of that reactant. Okay? And to describe the overall order of the reaction, you just add those together. So N plus M equals the overall order. So you would say, for this reaction, the order of this reaction with respect to A is N. And the order of this reaction with respect to B is M. And the overall order is N plus M. Okay? Now, many reactions can go beyond that. You can have more than 2 reactants, but I think 2 is probably as far as we want to stretch it, particularly in a general chemistry class. So let's just check. How do exponents or orders in a rate law compare to coefficients in balanced equation? They don't. They have no relationship at all. They're unrelated. Why? Because the balanced equation is only an expression of stoichiometry. Moles of this plus moles of that yields moles of product. And that's overall. It says absolutely nothing about the rate.
So the order won't affect our rate answer?
The orders, no, the orders are integral to the rate. The coefficients have no bearing on the order. That's the point I'm trying to hammer home here. So that you don't write a balanced equation and think that you can take the coefficients.
Add those to the balance so we can have balance.
No, they have no relationship at all. A balanced equation, if you had something like this, yields products, these N's and these M's have no relationship to one another. They do not mean the same thing. Maybe I'm hammering it too hard. Okay, so now how do we recognize these different orders? What values of N, what values of M? Generally speaking, you can have zero order, you can have zero, you can have one, you can have second order. Anything beyond that is outside the realm of this course. So we're going to focus on these three. They have certain characteristics that can be recognized if you plot the data. Okay? So, now I know I mentioned earlier, here's where you could get confused. I mentioned earlier that we use the method of initial rates to tease out information. But we also use the entire data set that I showed earlier with the NO2, the data set over time. If you plot that, irrespective of the initial rate, because we're watching it over time and we're getting product over here, but we're still watching the disappearance of the reactant. Okay. If you do that, that's what we're talking about here. So that rate is going to be, with the zero order, let's see, I'm going to put, spread it over here. I think I'm going to start about right here. So for the zero order,
So the reason it's K is because anything with the zero power is 1. The reason why it's just K
yes.
sounds 1. Is that it?
Right.
It's that simple? No other
Nope.
Okay.
Zero order equal to K. So what does that tell you? The rate of the reaction is not dependent on the concentration of the reactant. It's going to proceed at its rate regardless of whatever the concentration is. Doesn't matter. That's a zero order. So how would that plot? Let's see. I don't want to get ahead of myself. Yeah, it's coming. Coming on the next slide. So this is the rate expression. Rate equals K, equals the constant. The integrated rate law, and I don't have time to show you how we got there. Just take it on faith. Or look it up in Blackboard, because I've got the PDF files showing you how they're derived. Right? So if you've had any introduction to calculus at all, you may understand how they're derived, but only if you're really curious. So the integrated rate law, rather than being rate equals something, the concentration at a certain time is equal to the K value times that time, you know, how far down the line are you, plus where did you start from? This in here. So what this means is this is the initial concentration. This is the final concentration. This is your rate constant, and that's how long it took you to get there. So notice the form. Straight line. So if you plot A against time, you'll get a straight line with a negative slope M. So that just means do this, this, and over time, your concentration of A, it's a negative slope, right? So it's going to be like this.
And it's always going to be negative?
Always.
Okay.
For a zero order reaction.
Okay.
Yep. And the slope is going to be negative K. And wherever it intersects here, that's your initial concentration, your starting point. And this is whatever it happens to be at time t. Here, time t would be here, right out here, here. So it's gradually decreasing. Okay, so that's the zero order. So what that says is, if you plot, you have a series of concentrations and times at 0, 1, 2, 3, 4 minutes, say. Whatever that happens to be, and you have concentrations here, you plot those, they will be a straight line. If that's the case, if you plot these against time and you get a straight line, it's zero order. Okay? That's one way. You do that first. Just plot the data. Now, about first order. I'll leave these up here. Let's see.
Well, with the high half-life stuff, the initial A over 2K.
Oh, that's right. We got to get half-life. Excuse me. So, is everybody familiar with the concept of half-life?
Like how long a half-life?
How long does it take for half of the initial concentration to disappear? That's a half-life. It's similar to the half-life of a radioactive isotope. Right? How long does it take? Uranium, well, that's a bad choice. How about carbon-14? How long does it take for carbon-14, half of it, to disappear? That's the half-life. And for carbon-14, I think is in the neighborhood of 1,000 years for half of it to disappear. We use that in chemical kinetics as well. The half-life of this reaction, T1/2, is equal to the initial concentration divided by 2K. So if you know what the initial concentration is, and you've determined your K value, then the half-life is that divided by 2K. Notice this is an equation, right? So suppose instead of doing it that way, you determine what the half-life is. You look at your data and say, all right, in this amount of time, half of it disappears. And in this amount of time, half of it disappears. But you've already plotted your data, so you know it's zero order. Right? You know it's zero order, then you can use this equation and say, okay, so I've determined what K, actually, I don't have to determine what K is. If I know what T1/2 is, if I know how long it takes for half of it to disappear, and it takes the same amount of time for half to disappear, say if you started at 50 molar, right, at time 0, and in 2 minutes, you have 25 molar, right? Now, do we know it's zero order yet? Yeah, maybe not. But if it goes 2 more minutes, and now you only have 12.5 molar, then what's the half-life? 2 minutes. Because 2 minutes goes half here, 2 minutes goes half there. Half-life is 2 minutes. So 2 minutes here, and then the initial concentration, say 50 here, 2 here, then you can solve for K. So there's more than one way to get to K. Okay? And we'll have some problems that will illustrate that. I know I've got some in the review document that do just exactly that. So the important equations. This one shows you zero order. This one is the integrated. Right? This is the differential rate equation, and this is your half-life equations for zero order. Yep.
This might be a stupid question, but in you might already said it, but I just doing by me. How do you know when to use the integrated one? Or to just, I'm sorry. It's just copy.
Which one's easier to use? Right? Look at your data. What kind of data do you have? If you've got time versus concentration, I'd use that one. Because plotting that one tells you whether it's a straight line. If it's not zero order, it won't be a straight line, it'll be a curve. Okay, now the next one's going to be a curve. So the next one, the rate is equal to K to the first order. Right? You can't reduce that one any further. So this one does depend on the concentration of A, whereas zero order does not depend on it. Okay? And the integrated rate law here requires that you do a transformation to get a straight line. Right? So the integrated version here is going to be the natural log of A, not the common log, not the log, but the ln on your calculator. The natural log is equal to minus kt plus the natural log of the initial concentration. Yep. You found it?
No, but isn't the log and the ln kind of the same thing? Technically? Both says
It's a different base.
the log is 10 to the 10th power.
Log is base 10, ln is base e. Okay. So if this one is, let's see, log of x equals y, let's make this one log of a equals b. Then resolve this one to power, it will be 10 to the y equals x, and this one would be e to the b equals a. Different base.
Will we have problems where we won't have e as the base and
Yeah, possibly.
we have to do it long way around?
Well, for this one, you have to know how to use your calculator, right? Because it'll have ln. And then probably a shift key from ln will be e to the x. So you go backwards, right? The anti-natural log. Rather than 10 to the x, it'll be e to the x. Is that on there?
No, yeah, I do have it on there. I've done problems.
Okay, good.
Anti-understand.
So what does this mean? This means that in order to get a straight line from first order equation, you have to plot time and the natural log of A. If you do that, then you get a negative slope. And this is going to be a natural log of the initial concentration with a slope of minus k. Right? So the only way you get a straight line out of this one is to do the natural log transformation of your data. You leave your time alone, but you just transform the concentrations into the natural log. Right? So if you have a data set of time and concentration, you'll have, say, time here, then you'll have concentration here, and then this one you'll do a log transformation of these numbers, right? So then you would plot these against those. So what's shaping up is you get a data set of time versus concentration, and then you might as well just go ahead and plug it into Excel and tell Excel to calculate natural logs here. And then second order, I might as well put it up here while I'm talking about it. Second order is going to be an inverse. So you just do these transformations in Excel because it'll do them quick, fast, and easy. And then you plot this one. Is that a straight line? Nope. Plot this one. Is that a straight line? Yep. First order. Plot these. Is that a straight line? And these aren't. And it's second order.
So first will be a curve? Like
Yeah,
factor?
right. If you plot this data and it's really first order, it's going to be a curve.
Like, or will I draw it?
It'll probably go like that.
Should that again? Like, away.
It'll probably be like that. Okay, so there's your log transformation. No, I think it'd be the other way. It'll go like that. Because your log transformations make negative numbers. And these values in here are not going to be concentrations. They're going to be logs of concentrations. So you got to prepare your mind for that. Might twist things around in here. You're plotting the log of that value, not the value. And this one also has a half-life. T1/2 of this one, for the first order, is simply 0.693 over K.
Why is 0.693?
That's what it is. So here, all you need is, if you can determine the half-life from your data, and you know it's first order, then you can solve this and find K. You don't even need the concentration. So the half-life for first order does not depend on concentration at all. Only depends on the inverse of K. And then the last one we're going to look at is second order. Okay, so this rate will be K and A to the second order. Okay. And this one's going to be the inverse transformation of concentrations. But it's going to be a positive T, a positive K.
It's because it's the inverse, right?
Yeah.
So the graph go will be.
Oh, I left out
Probably the first time that it should go up.
Yeah, it'll go the other, right. It'll be a positive slope. Okay, let me see what was going on here. I missed a slide. First order reaction, 35% complete at the end of 55 minutes. What's the value of K? All right, so we're going to work the problem in here. First order reaction, 35% complete at the end of 55 minutes. So if we're saying that T0 is here, and at 55 minutes, what's the concentration? So we know it's the first order, so that means this is a little complicated. I probably shouldn't put this slide up here. Anyway, this is our integrated rate law for the first order. And here we're just arranging. I'm putting the logs on this side and keeping the K minus KT on that side. That's the only thing we did in this step. And then, if you remember logs, when you have a log of something minus the log of something else, it's the same as the log of the quotient of those two. Remember that?
Log rules.
Yeah, log rules. Okay. Then, if we solve this log, we're saying e to that power is equal to this. Right? Just like I put up here, what does a log mean? It means the base to the answer power is equal to the value that you're taking the log of. So that's all we're saying. There's an e right here, so we say e to that power is equal to this expression. Right? So we're just converting. Actually, we're taking the anti-log. So now that we know that this ratio is equal to that value, then we can use 35%, find out what 35% complete means. Okay. 35% complete means that 65% of A0 is still A.
How Use times by 2. Because half.
No. 100 minus 35.
Oh, never mind.
So we're saying that if we're saying that it's 35% complete, that means we've used up 35% of the initial amount, and what's left over is 65% of what we started with. So that's what A is. Right. So at 55 minutes, A is equal to 0.65 of the initial amount. Right? Because we've used up 35% of it, so 65% is what's left over in fractional terms. Right? So this ratio then is 0.65. This ratio is 0.65. So if we set 0.65 equal to this value, then all we have to do is plug in the time value, which is 55, and we can solve for K. And K is 7.8 times 10 to the minus third reciprocal minutes. Okay. So, yeah, that's K. All right, now let's go back to second order. All right. See if we still have an audience. Yeah, we got an audience there. Okay, second order. So second order is going to be, this is the rate law, this is the integrated rate law, differential integrated. And to get there, if we plot the data, let's see. If you plot the raw data, it's going to be a negative slope also. If you plot the log data, it's going to be negative, but it's going to be curvilinear. That is, it's not going to be a constant slope. But if you take the reciprocal, you get a straight line, a positive straight line. Okay?
So I had a question back to Paul. What is the minute minus 1 mean?
Reciprocal minute?
Yeah.
Well, that just means the minutes in the denominator.
Okay.
When you bring it in the numerator, you have to give it a negative sign. Power, negative power.
Wait. Bring the denominator.
When you say, if your value, if your unit of measure is something here, whatever it happens to be, so you got X per minute, then you bring it into the numerator, that makes it a negative sign.
Okay. Thank you.
Okay. Okay?
Why is it just, doesn't matter, it's just -1 for that one? Is it always goes from minute -1?
Yeah, if it starts off in the denominator, when you put it in the numerator, it's a -1. That's what that means. Sometimes it's more convenient. If you're going to write out a number, constant, whatever it happens to be, if you've got a complex unit of measure, where something in the numerator, something in the denominator, sometimes it's more convenient just to write straight across. And to do that, you have to change everything that's in the denominator to a -1 sign.
Oh, it's just, okay, I see what you mean.
Okay? Yeah. Okay, so we plotted the time against the reciprocal there, and we get a straight line. And where it intersects here is the reciprocal of the initial concentration, and the slope is a positive K. Right? Let's see. Oh, there's a half-life. Okay, and then the half-life for this one is equal to just 1 over K times the initial concentration. All right? So you'll notice about all three of these half-lives, they're all proportional to the inverse of K. K's in the denominator, K's in the denominator, K's in the denominator. Whereas this one is proportional also to the initial concentration This one's not proportional to any concentration. And this one's proportional to the inverse of the concentration. Okay. So there you have your differential, integrated, half-life, those three. And I've got them in a table. I think one of the next slides, put them in a table. Where's that? Maybe it's in your, must be in your text. No, there it is. Yeah, we'll get to it. All right. So let's see. Let's make some room here. And leave this stuff up here, just in case we need it. Oops. Too far. Yeah. And then we can work on this problem. So we have a reactant yields products, and the initial concentration is 5 molar. The first two half-lives are 25 and 50 minutes. So let's see, what does that mean? A concentration and time. So we have an initial concentration of 5 molar at time 0. The first two half-lives, after 25 minutes, how much A do we have left? Half of it, right?
Right.
2.5.
I think the A is 0 times was 5.
No, that's the beginning. A0 is the initial. Yeah. A sub 0 is always the initial. This is where we're starting. And the first half-life is 25 minutes. So that means after 25 minutes, you got half left, 2.5. Right? Second half-life is 50. That means we go 50 minutes more, which means we're at 75 now. Okay? This is the second half-life, and it's going to be half of this one, 1.25. Okay? That's key to answering these questions because you've got to construct the reaction table correctly. First half-life is 25 minutes, that's easy. Getting the second half-life in there and realizing that it's actually, if you were timing this experiment, you have to stop watching. It would go 25, you'd have that much. And then 50 more, you'd be at 75. And you'd have that much. Okay, so that's the structure of your reaction table. Write the rate law for this reaction. Calculate K. Blah, blah, blah. Okay. So the first question you want to ask, let me see. Be sure I'm logical here.
What's Q?
Okay, it's on the next slide. First thing you say is, if you notice here, that these two are dependent on concentration, whereas this one's not, right? So, is your half-life dependent on concentration?
No. Maybe so.
Yes. Why? Because the first half-life is 25. The second half-life is 50. The concentration here is 5. The concentration here is different. So it has a different half-life. Okay? So that's the first clue. It can't be first order because it depends upon concentration. If it didn't depend on concentration, then the second half-life would be the same as the first. Right? If the second half-life was also 25, then the concentration wouldn't matter. And it would be the same, it just keep going down. Every 25 minutes, you half. But for this one, the half-life length, this value, does depend on concentration. So that means first order is out. Can't be first order. So that eliminates a third of our possibilities. If the rate law were 0, if it were this one, then T would be, T1/2 would be A0 over 2K, right? So what does that mean? Well, if we do the calculation, right, A over 2K, and we put in 5 for our initial concentration here, and we calculate what's K, right? K then would be 2 times, let's see, move the 25 over here and the K over there. That's what we've done. So 2 times 25 is 50, and 50 into 5 is 0.1. So K would be 0.1 if this were 0 order. Well, if it's 0 order, then you should get the same K for the second calculation. So if we say we're starting at 2.5, right? And our half-life is 50, right? So half-life is 50 equals 2.5 is our initial now. So our initial is actually changing for this reaction. The initial concentration for the second half-life is 2.5, not 5. So the second calculation says the initial is 2.5, and the half-life is 50. Solve K is 0.025. It can't be 0 order because K is a constant. Okay? So that means it has to be second order by process of elimination. But we can check it to be sure, right? If we use this half-life right here, and we do the same set of calculations, we find that doing the same set of calculations using the second order, we get 1 over 125, and for the second half-life calculation, we get the same number. Okay. So K then is 1 divided by 125 for this value right here. Okay? It's a little detective work.
So far, this seems easier than watching calculations.
I hope so.
Yeah, it was throwing me off a little bit until you started getting into this part. So I mean, it's starting to come together.
Yeah, I mean, when you first are introduced to kinetics, it just like this, huh?
Also, it helps it's only one chapter.
Yes. Yeah, we're just sticking to one chapter this time. And notice that we're doing, let's see, what's the next chapter is equilibrium, isn't it? Yeah. 12 is kinetics, 13 is equilibrium. We're doing kinetics first because equilibrium depends upon kinetics. Okay, so the rate law, when you write the rate law, you know now that it's second order. So the rate law is going to be A to the second order, and then we just substitute the K value. Well, we should have written this in here for the K. It would be rate equals this times that squared.
You're going to add the that's molarity, never mind, sorry.
Yeah, molarity. It's there.
Sorry.
Okay. So, well, that's a good question. So if we write, let's check ourselves. Rate equals 8 times 10 to the minus third, molarity to the minus 1, minutes to the minus 1. And that's times A squared. Let's check ourselves. Rate is going to be in terms of molarity per minute. Change in molarity, right? Change in concentration per change in time. So this should be molarity divided by minutes, the rate. It might be negative, it might be positive. We're only interested in the absolute values of these right here. So if we say this is molarity to the minus 1, minutes to the minus 1, A is in what units? Molarity, right? concentration and molarity? Well, it has to be. There's no other choice. Well, if we square that, which is what that does, then one of these molarities cancels with this, right? Because this means it's in the denominator, right? Then one of these cancels and leaves us another one. So minutes is in the denominator, and molarity is in the numerator. So we've got the right units of measure. Just checking. Okay? I'm still thinking about it. I'm just checking to be sure that our units are right. So I moved these down here into the denominator, just so it showed cancellation. This is in the numerator. Since this is molarity, it's molarity squared. That means you cancel one of them, you still have one left. Right? And this is still in the denominator. So this numerator, denominator, numerator, denominator. Okay. So I think we're good. Okay. Oh, and then we're going to use the rate law to calculate A at t equals 525 minutes. So if we use the integrated second order rate law, why do we use the integrated rather than the differential?
Because if you have time involved.
Because time, yes, exactly. Time is involved. So if we use this calculation, then we have our K value here. We have the time elapsed, 525 from 0 time. And from 0 time, we're starting at 5, right? Because that's time 0. And this is sometime after time 0, right here. Then we can calculate our A value. And we know that at 525 minutes, our concentration is 0.23 molar. Okay?
But how do we get 0.23?
Well, if this is 1 over A, and that's 4, then you just invert both sides of the equation. So that makes this A, and that makes this inverse of 4.4. So take the inverse of 4.4. Or just say 1 divided by 4.4. If you can't find your inverse.
That works.
It should be 2.23.
Yeah.
Okay? If you do the same thing for an equation, if you do the same thing to both sides, then decide. You can add the same thing to both sides, you can divide or multiply both sides by the same thing, or you can invert both sides. It's valid algebraic technique. Okay, so there's everything in one slide, answers to all our questions. I'm going to get a video. Let me see. Or do I have to click it? Yep, I'm not going to give it to us. That video crapped out. Okay, so let's move on. So how can you tell the difference between, among, excuse me, my English teacher would slap me in the face, among 0 order, first order, second order rate laws from their graphs? From their graphs. How do you tell from their graphs?
Which,
Remember, you set up this one, and you do that one, and you do this one, and you do this one, and you graph this pair, and this pair, and this pair. And you look at the graph, see which one's a straight line. So if the rate equation is dependent on the concentration of two reactants, I described this earlier. Okay. This is just puts it on a slide for you. So what do? What you do is, since we're interested in these are expressions of zero, first, and second order in terms of one reactant only. Then you increase the concentration of the second reactant so much that it effectively stays constant
This is like a
during the
bleaching
reaction.
dye that you compare it to. Right?
Yes, right, exactly. And we set up what we call a pseudo rate constant. So this is what it would look like. Right? So if this is the bleach, fortunately it's a B, then this term and that term create a new constant value right here. And then we let this one change. We measure the disappearance of our blue or red dye, whichever one you choose, over time. Plot the data, plot the log of the data, plot the inverse of the data, and see which one is the straight line. And that will give you the order of the reaction with respect to the dye, or A. So I left the complete discussion of this process in your kinetics lab for next week. Right, so you can dig into that. There'll be a better explanation of these terms. So for the lab next week, just be sure that you know how to conduct the experiment. That's what I'm interested in. We'll deal with crunching the numbers afterwards. Okay, so here's everything in one big swoop, and it came straight out of your textbook. Okay, so let's see, this is another, oh, here it is. So what we're saying here is, this reaction, we start off with 5 molar, and our K is this value. And just let the units for K be whatever they will. We're more interested in what does the concentration look like after 30 seconds, if it's a 0 order, a first order, or a second order. Right? So if it's a 0 order, our rate law is going to look like, our integrated rate law is going to look like this, right? Just the raw data minus K. We plug in the numbers, right? Here's our K. We're going to use that same value for each one. We're going to do the same thing for each one of these and just see what's left over after 30 seconds. And if it's 0 order, you still got 4.7 molar left over. So quite a bit. So it's a slower reaction, I would think. If we did first order, right, we'd take the log, natural log of each of these values, and then eventually solve for A. Right, so we had to take the antilog of 1.309. 3.7 molar. So if it's first order, it's moving faster. Over that same period of time, you have less. Everything else being equal, first order is faster. Second order, here we go. Second order, right? Just plug in the numbers like we did before, and we find out that second order gives us even less over the same period of time. So that sort of intuitively makes sense to me. 0 order is slow, first order is faster, second order is faster than that. Okay? So now let's say a few words about the mechanism. Let's see, I'll erase this. And, oops, this one is. Anybody remember what this one is? Just checking. I'm gonna leave this space empty. Leave that stuff up there just in case we need it. If I have to, I'll erase that. Do you break?
Yep.
You guys need a break?
Okay, I don't care. I'd rather just get through it.
Okay. Okay. We got a roll going here. Let's keep it going. Reaction mechanism. Like I said before, most reactions do not occur in a single step. Some of them do, I'll admit. But most of them occur as a series of elementary steps. That's what we call it. So the overall reaction expression, reactants, yields, products, is actually 2 or more elementary steps in between. Okay? So in each case, we form some form of intermediate in one of the steps. But that intermediate is used up in a subsequent step, and you never see it in the products. So that's the trick, trying to figure out what's the intermediate that helps explain the overall reaction.
Definitely sounds like groups.
Mm-hmm. Yeah. So here's an example. Say we're going to react that nitrogen dioxide, but this time we're going to react it with carbon monoxide. And that gives us nitrogen monoxide and carbon dioxide. Okay? So this has actually been determined. This is the best series of elementary steps for this reaction. It's already been done for you, so we can use it as an illustration. So what happens first is we take nitrogen dioxide and react it with another one. Okay? And when we do that, we get one of these oxygens transferred over here. This gives us nitrogen trioxide and nitrogen monoxide. Okay? So that's our first elementary step. But now this, of course, is found in the products, but this is not. That's our intermediary, or intermediate product. So now this reacts with carbon monoxide, see, because this step doesn't include carbon monoxide. Now we're going to react it with carbon monoxide. We're going to transfer one of these oxygens over to the carbon monoxide and make carbon dioxide. And now we have regenerated nitrogen dioxide. Okay, so how do we know the overall reaction for this one? Well, if we write it out as this plus this yields this plus this as our first step. Step 1, then step 2 is this from over here plus this equals nitrogen dioxide plus carbon dioxide.
Right, so,
These are 2 steps.
what's just the N of 3 if there's no N of 3?
That's the intermediate, so you
Yeah, that's the intermediate. There's an intermediate.
This is like the beginning of, this is what we start with, and this is what we're ending with, but we don't see what happens in the middle from what's up there.
Oh, this is the middle.
Right?
Yeah.
So this is the overall, and this is one of the conditions for your proposed elementary steps. You have to be able to add them together and end up with the overall reaction. So ideally, you know the overall reaction because you've determined it independently. You know that if you put this, a mole of this together and a mole of that together, you get a mole of that and a mole of that. You know that. This is the mechanism that you're proposing. So if we say this one, we can keep it. But this one is on the reactant side here and the product side there. It cancels, right? Remember Hess's law? Add them together. So reactant side, product side, they cancel. Product side, reactant side, they cancel.
Oh, so we did What's the change?
So that's all you got left. And that's the overall reaction. So the elementary steps have to add together to give you the overall reaction. That's the first condition for proposed elementary steps for a reaction.
Can I ask a question?
Sure.
How do you know NO3 was nitrogen nitrite? How do you know that was the one to use?
Because it says so right here.
Oh, and 3, yeah.
Yeah, we didn't include a legend. So you sort of have to deduce that this is the nitrogens,
Nitrogen two.
these are the oxygens, right? And if you do this enough, by convention, usually the blues are nitrogens, the reds are oxygens, the yellows are chlorine or halogen, things like that. If you have a stick model box, they'll be color coded when you start to put your models together. They'll have these color codes, and black's always carbon.
Okay, actually, in nitrogen's on the top, and then in oxygen, nitrogen and carbon's on the bottom. And
Yeah.
oxygen.
Right.
That's-
Yep. Okay. So we have elementary steps can be considered in terms of molecularity. Anybody? You're too young to remember MASH, television MASH. You watched the episode.
Actually, my mom wasn't sure.
There were 1 or 2 episodes where Father Mulcahy starts talking about something. I can't remember what it's about, but he uses the term jocularity. I don't know if you remember those episodes. But that's what I think about when I see this term, molecularity. It just makes me giggle. Molecularity is simply how many molecules are involved in the reaction, in the elementary steps, right? So if the elementary step is just one molecule reacting to do something, to make a product, then it's unimolecular. If it requires that you have 2 molecules coming together in an elementary step to produce something, it's bimolecular. And if you have 3, it's termolecular. Now, in terms, here's where we sort of disregard what was said earlier. You have to determine the overall order of a reaction experimentally, right? But when you start talking about elementary steps, you can say that if it's unimolecular, that's a first order reaction because there's only one molecule. So the relationship between our previous terminology and this discussion is that unimoleculars are first order. Bimoleculars are second order. So you have the order for one and the order for the second one combined overall is second order. 1 + 1 is 2. And if you have 3 coming together, you're talking about third order, and we didn't even talk about third order.
So don't worry about terminology.
Just realize that termolecular is highly unlikely, very rare. Think of it in these terms. When 2 molecules, or when a molecule reacts, if it's just me, I can react anytime I want to. I don't care about whatever's else going on anywhere else. It's just me, I can split. Okay? All right, so that's highly likely whenever I want to do it. Bimolecular is a little rarer, but not too much so. In order to have a bimolecular reaction, you need 2 molecules coming together with sufficient energy and at the right orientation so that the reaction occurs. So that's still fairly likely. But getting 3 molecules to come together simultaneously with the right amount of energy and the right orientation for all 3 of them is very rare. So when when a chemist proposes a termolecular step, an elementary step in a mechanism, better have a damn good reason for it. Because his colleagues are going to rake him over the coals if he's leaning too heavily on termolecular. If there are unimolecular and bimolecular steps to a mechanism that will accomplish the same thing, go for those, because they're much, much more likely. Termolecular is almost impossible. Okay, any questions about that? Right.
They've man-made termolecular, like, reaction?
My guess is yes. Yeah, somebody somewhere has studied termolecular reactions purposely. Yeah. Or had a graduate student do it for him, which is more likely. Unless he works in a government lab, then you're paid enough to do it yourself. So now to the question of overall rate of the reaction, right? What determines the rate of the reaction? Well, it's like any, say you're in a bucket brigade fighting a fire, right? And you're passing buckets down the line. And you got one guy that weighs 350 pounds and he's about to have a heart attack. And he just grabs one and just barely gets it past him to the next one. The overall rate for that bucket brigade is limited by the fat guy. Okay, so the slowest reaction, the slowest elementary step is the rate determining step.
It's like this during traffic.
I'm sorry?
It's like what you just said, but you think about it in traffic.
Yeah.
It's like where someone, like, if it's like while in traffic, like traffic stops, like slower, is like you have a bunch of people traveling on the road, but one person stops.
Mm-hmm.
That one stop, everyone else that comes to that one stop is going to stop.
Right, right.
And it throws off the whole train.
Or you have somebody just rear end somebody on this lane, that stops that lane, and you got to funnel both lanes over into this single lane. That slows everything down. Yes. So we've already talked about this one. The sum of the elementary steps must give the overall balanced equation. You got to be able to add them up and get the overall. And the mechanism has to agree with the experimentally determined rate law. So what that means is if you determine the rate law here, then the slowest step determines the rate, and the slowest step has to agree with your overall rate law.
Why the slowest? Because
It's the rate determining step, right?
the slowest one determines how fast or how slow it's going to be in like a total. Okay.
So usually there is a rate determining step, and the others are generally very fast, just quick. As soon as something, say we had 3 steps, and this was the slow step. This one's going to be fast. This one might be super fast. So whatever your reactant is here, it goes almost immediately to here, and then it just chugs along. And as soon as something's produced over here, it just spits it out fast. But it can't react. This one can't happen until that one does. That's the rate determining step. And your mechanism has to agree with the rate determining step. And I don't think this one's going to work either. No. Oh well. I'll eventually do something about that. So let's say we're going to decompose N2O5. And the overall reaction says that 2 moles of this yield 4 of this and 1 of that. Right? And these are all in the gas phase. So if we propose that this step is fast, we're going to take one of these and make NO2 and NO3. So here's an intermediate that we got to use up somehow, because this one is over here, this one's over here, so we could keep those if we need them. So in the second step, we're going to take this one and react with that one. So we're going to use it up. Okay. And we're going to produce this one, and that one. So this one goes into the reaction, spits out over here, but in the process, it takes this one and converts it into that one and that one. That's the slow step. This one is also a fast step where we're taking NO3 plus this NO. Let's see. Now the question is, I don't think we're finished with this yet, right? Because we produced this one here, but we used it here. Now where'd this one come from? Plus this one. Right, where'd that one come from? Well, that one came from here to produce this one. All right.
Did they?
It's not balanced yet, right?
Yeah.
That's the only thing that makes sense. These are rate steps, but they're not balanced yet. So we can't add them together and get this. So what we have to do is we have to modify this one, right? If we do multiply 2 times that, that gives us 2 of these. Okay, so we're good there. And we can only do that because N2O5 does not appear anywhere else in here. So it's going to produce 2 of these, 2 of those, 2 of those. And that gets rid of these 2, those 2, that's good. And that gives us 2 here. But these cancel. Those cancel. And that leaves us starting with 2 here. And 2 here, oh, and 2 there. Okay, so we're good there. And then 1 here. All right, so all we had to do was multiply that first step by 2. And that allowed us to balance the equation and add them together and give us this one here. So I guess the moral of that story is it's okay to use multipliers as long as you multiply by the whole. This is a step, but we can't add them together until we're sure that they're going to add together and equal that. There we go. Okay, so we've got a reaction that we're calling A plus 2B equals C. So we're proposing a mechanism where 1A and 1B comes together to make a D. And then this intermediate, and that goes really fast. So virtually all of this produces that. And then the slow step is we're going to react this with some more of the B to make our C. That's the slow reaction. So what would be the rate law for this one? Well, okay. So what's the molecularity? Yeah, that doesn't work. The order of the reaction in terms of A for this mechanism, there's only 1A, right? So it has to be first order. There's only 1A. But there are 2 B's here in the mechanism, right? So that's a bad example. You know why? Because A to the first power says that's 1, and A to the second power says that's 2. Right? So the author should have picked something else that would not be a direct relationship between 1, 2 and 1, 2. You know, that's misleading, I think. As long as you recognize that the rate law has to be dependent upon this step. But it's not obvious that it's that either. Bad example. So don't expect to see that one on any test.
Thank God.
It's a bad choice. Okay, so I made reference earlier to what we call that collision model, where we're talking about unimolecular, bimolecular, intermolecular, where things come in and smack together. Right? Conditions. When these molecules collide, and of course if it's unimolecular, it doesn't matter. So the energy that's involved in the unimolecular reaction is just whatever makes it jiggle faster, and then it just flies apart. But there is an activation energy for that. So the amount of energy required for the reaction to proceed is called our activation energy, E sub A. When you have a bimolecular, it may incorporate some vibration plus collision energy, right? And that's directly related to temperature. The other factor is molecular orientation. In other words, if the reaction is going to involve a part of the molecule that's on this side and they hit this side, it won't happen. So the collision model says that you have to have the right energy and you have to have the right orientation in order for a reaction to occur. Okay, so I know this one's not going to work. So what we have is in graphic terms, is what we call reaction progress. So the progress of the reaction in this direction, and the energy of the components is in this direction. So if we start off at this level with our energy of our components, right, and we end up way down here, that means if we start off at high energy, end up at low energy, where'd that energy go?
The reaction.
It was given off, right? It's not in the reactants or the products, so it has to be given off either as heat or light or some other form, right? So if the reactants are here, and the products are here, what this potential energy diagram is saying is when the reactants either come together or if it's unimolecular, gets energized, the energy added into it reaches a peak. And this is what's known as the transition state, because it is transitory. It doesn't last long. The transition state or the activated complex. Right? Once it reaches this point, that means it's got enough energy to go down the other side of the slope, and it goes down here. It becomes product. Okay? So the amount of energy required to go from reactants to products, the activation energy is here. So it started here, you have to add energy to get to this point, and then it runs down the other side. Okay? Now, what's this difference right here? That's the enthalpy of the reaction. Right? Didn't we do that didn't we use the styrofoam cups and measure heat of reaction last semester?
I think so, the colorimeter.
Yeah, calorimeter.
Yeah.
Yeah. That's what we were measuring here, this part. The delta H, the enthalpy of the reaction. We didn't measure this part. You can calculate this part, And I'll show you in a second how to do that. But while we're here, what if the situation's reversed? What if you have products? You put products into your reaction vessel and you want to get reactants out. What's the activation energy of that reaction going back this way? It's more. It takes more energy to activate the reverse reaction because you got to go from here up to there. You have to go to the same activated complex to get back over the hump to go down here. Okay? So this is how we make nitroglycerin. We put reactants together here, heat them up, and then they go, actually, for nitroglycerin, let's reverse it. You go here, reactants, and you go up like that, like that. So you put all this energy in, and it's sitting there just waiting for somebody to whack it with a hammer or jostle it the wrong way. And then all that energy is released. Okay. So we said this before. You got to have enough energy to produce the reaction. It has to equal or exceed the activation energy. Okay. Then you have to have the correct orientation of your reactants in their elementary steps in order to produce the new bonds. They've got to be oriented correctly in order to do that. Now here's the Arrhenius equation. Name was Svante, S-V-A-N-T-E, Svante Arrhenius, who studied reaction kinetics and proposed this equation. So this constant value, which is different for different reactions, is equal to this term, which is his for the frequency factor, that is how often do collisions occur. And then E is just that, the base of the natural log, to this power, the activation energy divided by RT. R is your gas constant, the one with the energy term in it. And then temperatures in Kelvin. So this by itself is not very useful, right? Because we don't know what K is, we don't know what A is. Of course, we can measure temperature, and R is a constant. So we need another way of expressing it. So this is the linear form, or for lack of a better term, integrated form of the Arrhenius equation. And this gives us the K. Well, actually, we do know what the K is. I misspoke. K is your rate constant.
That K was the
Is the what?
time.
No, T is the time.
Oh.
Little t is the time. Big T is the temperature.
Oh, okay.
Yeah. K is
Kelvin.
junk calls. All right, so K is your rate constant, and A is the one we don't know. Okay, so then we use the integrated rate law. Because if we measure the rate constant at different temperatures, so this is your Y term, this is your X term, measure the rate constant at different temperatures, at least two, then you can determine what the slope of the curve is and equate it to this value and solve for your activation energy. Okay. So there you go. If you actually do that at two different, well, this one was done at 1, 2, 3, 4, 5 different temperatures. So the more points you have, the better, actually. Then the slope of the line is log K over 1 over T, changing 1 over temperature. Then you get this, because this slope is 1 over T. Let's go back. Here we go. Right, this is our x. Right. So it's going to be here. 1 over t is our x value, and log k is going to be this value. So we determine k for each one of these experiments, rate constant. Plot them, find out what the slope is, and the slope then is equal to minus e over r. Once we know what the slope is, we can solve for e sub a because r is a constant. Okay? So that's the form of the Arrhenius equation that we would use to solve for the activation energy. So, I don't know if you've ever heard this. If you've taken biology, you've probably heard this. For every 10-degree increase in temperature, reaction rate doubles. That's just a rule of thumb. So that's why if you decrease the temperature, if you don't want your food to spoil or your samples, your tissue samples to spoil, you decrease the temperature. Right? You freeze them. So as you go down, every 10-degree decrease, so at room temperature, we're like, say 20 degrees to make it easy. So you go down to 10 degrees, reaction rate cut in half. Go down 10 more, that makes it cut in a quarter from the original. So you keep going down, eventually you reach a point where the reaction rate is vanishingly small. So that's why tissue samples that we collected for the USDA, we froze them in liquid nitrogen at minus 195 degrees centigrade. So there's virtually no reaction going on. And then we stored them, we freeze dried them then and ground them up, processed them, and then we stored them at, one second, let me think, minus 100. Yeah, minus 100 degrees centigrade. Once you get them stabilized, liquid nitrogen, grind them, freeze dry them, grind them, then you can keep them for a long time at minus 100 degrees centigrade. So we had freezers that were built to maintain that temperature. But if we take the rule of thumb and we say we double the reaction for every 10-degree increase, then what would the activation energy for a reaction have to be in order for that to be true for 25 degrees to 35 degrees, that 10-degree difference? Right? So it's really actually quite simple. We're saying that for this reaction, 298 K, versus this temperature, 308 K, this has one reaction rate, and the higher one has a different reaction rate. But we're saying that the reaction rates are related because the second reaction rate is twice the first one, right? So this one is actually 2 times the first one. Okay, then we can take the ratio of the two, right? Because we say the ratio between the two is actually 2, right? Double the reaction if you increase the temperature 10 degrees. And each one of these Ks, then these rates is equal to these values with the temperature. The only difference here is the temperature, right? A's are the same, E's are the same, and this is a little exponent logarithmic type transformations. A's cancel, and then E to this one minus this one, right? Because it's in the denominator. So that's why that's a plus, it's a minus a minus. So there we have our power of E, and we consolidate forms and we find that 2 equals E to this. Now how do you resolve that one? Logarithms is the best way. So we take this one. Let's see, do I have arrows going? No, I don't. Okay. So I'll just have to show you. So now we're going to go from this step over here. So we take the log of both sides. And in the process, I move that R over here. Right, so log of 2 times R equals this term. And then you just solve. Work your way down. And you find that the activation energy for that rule of thumb to be true the activation energy of the reaction has to be 52.9 kilojoules. Not that it makes much difference in the real world. But any difference from that, activation energy was higher, was lower, it would change that rule of thumb. It wouldn't be 2 anymore. Okay, so I think this is our last discussion. It has to do with catalysts. What does a catalyst do? And I want to make some more room here because I want to discuss catalysts in terms of that reaction progress diagram.
Isn't that what like starts the reaction? Catalyst?
Actually, no. The reaction will proceed without the catalyst, right? So if we have this and progress here, again, progress, it's messy. Say we're just going to do this and this, like that. Then if we're starting out with reactants, the products, without a catalyst, we have an activation energy of this nature. Okay? With a catalyst, what a catalyst does is it provides an alternate one or more elementary steps in between from here to here. And the elementary steps provided by the catalyst have a much lower activation energy. So for a catalyst, we might just go up like this. And this would be our new activation energy for a catalyst.
So they need less energies that will activate and they help.
Correct.
And they help bring it faster to really good.
And because the activation, right, because the activation energy is lower, the reaction proceeds faster. It doesn't change the overall delta H for the reaction. It's the same enthalpy for both ways. It just happens faster. And it happens faster because we provided an alternate pathway, different elementary steps to get from here to here. There, that's what it looks like in the diagram. Yeah, theirs is going the other direction, but that's okay. Now, another way of looking at it is how much energy is provided to the, at the same temperature, how many collisions are there that have enough energy to proceed? Uncatalyzed reaction, you have a certain amount. Right? So all of the collision energies are in here. Low energy, more. You reach a certain point where you've got enough energy for the reaction to go. But what happens is, with that same distribution of energy, we just move the bar left. So the catalyzed reaction has a lower activation energy. That means more collisions produce reactions. It's another way of looking at it. Now, what types of catalysts are there? We'll go with the heterogeneous catalyst first. The heterogeneous catalyst is one in which the catalyst exists in a different phase than the reactants. The best example of that is the catalytic converter in your car, in the exhaust system. Of course, everything coming out your exhaust is a gas, but the catalyst is a solid. There's little ceramic beads coated with platinum and palladium. Right? That's more efficient because you really only need that surface contact for the catalyst to work. You don't need solid beads of platinum or precious metal. It's a good thing because if thieves knew that were the case, they'd be under everybody's car swiping their catalytic converters. So the phases are different. You have a solid phase catalyst and your reactants are gases. And what happens is, in that case, the reactants are adsorbed to the surface of the catalyst. And what that does is it fixes their orientation. So at the same energy level, they're properly oriented so that more of those impacts produce reactions. We also do that with partially hydrogenated vegetable oil. They use a catalyst. They take oils with double bonds in, lots of double bonds. In the fats, and they hydrogenate them. Right? They add extra hydrogens, get rid of that. What that does is it makes the melting point of your oil higher, so you can heat it to a higher temperature, and it still functions. They have a lot of double bonds in there. The smoke point is a lot lower, and your oil doesn't last as long. So for a business, that means money. But those are also heterogeneous catalysts. Of course, the converse is homogeneous catalysts. So there's your catalytic converter. Homogeneous catalysts are those in which the catalyst is in the same phase as the reactants. Okay? So let's see. I missed saying another thing about catalysts. Catalysts participate in the reaction, in the elementary steps, but not consumed. That's important. They participate in the reaction, providing an alternate pathway, but they're not consumed. In other words, they may be part of the intermediates in the elementary step, but on the product side, they're reconstituted. So overall, you don't see any change in the concentration of your catalyst. Goes in one end, comes out the other. So what would be like the same phase? How about hydrogen peroxide? Okay. And it naturally decomposes over time into water and oxygen. Okay. So this would be an aqueous solution, and this would be a liquid, and this would be a gas. Okay. So that's the uncatalyzed reaction. Let's see, we've got 2 hydrogens, 2 oxygens. Oops, I need to balance this. Let's see. 2. Like that. 4 hydrogens, 4 oxygens. So that's 2 and 2. Yeah, there we go. Okay. So that's the balanced decomposition of hydrogen peroxide. So you know, if you keep hydrogen peroxide on your shelf, the 3% version, for a long time, it kind of loses its oomph. Right? It's gradually converting into oxygen. If, however, you can do this 2 ways. You can do it with an inorganic catalyst, or you can do it with an organic catalyst or enzyme. Let's see, I don't have that description here. But what happens is, if you put potassium iodide in that solution, the reaction goes bam, just that fast. I mean, it just explodes. And it works better instead of that if you have 30%. It works really good. So if you want to try it, you can buy 30% hydrogen peroxide, and you can buy potassium iodide easy enough online. And you put some of this in a 2-liter bottle, and a little food coloring in it, and some soap to make it sudsy when it comes out. And then you take your potassium iodide solid, and you pour it in that solution, and it goes into solution immediately. It's very soluble. So the iodine is actually the business end. This is what does the catalyzing. And this forms your catalyst in the same phase as your aqueous. It's a homogeneous catalyst. Provides an alternate pathway and produces massive amounts of oxygen. So that's why it foams and goes, shoots right out the top, colored, whatever color you choose. One of my students at Southern, they were having a gender reveal party for he and his wife. So he got some of this and some of that, and he had his 2-liter bottle, and he poured the food color in there. Red would have been for girl, come out pink, and blue for boy. So he poured whatever color it was supposed to be. I forget what the sex was. And that was his reveal. He just dumped the potassium iodide in there. That revealed the gender. The other way is with an enzyme, catalase. Catalase will provide the same decomposition, but by a different pathway. Right? That's why when you put hydrogen peroxide on a cut, it fizzes, because every cell has catalase in it. And when the cell has been ruptured, like it is with a cut, you have that catalase there that decomposes the hydrogen peroxide and produces the oxygen. And one thing that most pathogens abhor is an oxygenated environment. Most pathogens like low oxygen or no oxygen, particularly things like Clostridium, or let's see, what's the one that causes gangrene? I think it's a Clostridium too. Or botulinum, right? They're obligate anaerobes, they call it. They don't like oxygen. So when you hit them with this excess of oxygen and it fizzes on your skin, you're killing all the pathogens. Of course, you only want to do that once, because it's also an extreme irritant to your skin, and you can start damaging good cells. But catalase is an example of an enzyme, which is a type of catalyst. We say it's an organic or a biological catalyst, but it runs deeper than that. Inorganic catalysts are simple mechanism enhancers, whereas enzymes are much more complex than that. They not only speed up the reaction, they direct the reaction. In other words, you can theoretically go backwards with this, but with catalase, you can only go one direction. You cannot go backwards. No. Yeah, I cannot. It's difficult, more difficult. You would need another enzyme to catalyze the reverse reaction, and that's the way our cells control reactions. They have two sets. They have one that goes this way and one goes that way. Okay, here's an example of a homogeneous catalyst in the upper stratosphere, right? We say ozone, O3, protects us from certain types of ultraviolet radiation. If you get NO up there, what it does is it catalyzes the decomposition of O3. So NO2 produces O2, and then you also get, this is a special class of type of oxygen called a free radical. You're going to have free radicals up there because of the UV radiation. So this is one reaction, this is another reaction, and when you combine them together, you get these are elementary steps, and when you combine those elementary steps together, you get free radical oxygen plus O3 produces O2, and you lose your ultraviolet absorbing capacity. There are other ways to do that. Chlorofluorocarbons, freons, they do the same thing. Right? Let's see. Nitric oxide. leads to the depletion of ozone. Free radicals are always going to be there. So what happens is when you produce this, when you send this NO up there, it produces NO2, and the, let's see, what goes in? NO goes in, NO comes out. Right, so this is your catalyst, NO. Recognizing the catalyst is important too. For the freons, what happens is light way up there in the upper stratosphere decomposes your chlorofluorocarbons and produces chlorine free radicals. And those free radicals cause the same type of decomposition. So in this case, your catalyst is chlorine free radical. Why do we call it a free radical? Because it has unpaired electrons. So a chlorine atom up there, that only shows the unpaired one, right? We know the chlorine has like that, right, 7, because where it is here. So the free atom is going to have this unpaired electron that's extremely reactive. It really wants to pair with something. So whenever you see a free radical, it's any molecule with an unpaired electron, at least one, could be more. Okay, that's it. Oh, how are we doing? I've been paying attention to time.
It's 11:10. Technically, we went over in the lab, but.
Yeah, that's fine. I was planning on doing that anyway.
Can I see your data from the lab?
Yeah. Okay, guys, we're done. Get well.
Dr. Roy, sorry that. What? Dr. Roy, yeah, it was too cold in here.